maybe a little odd. I had to make this joke because we talked about that. That was actually Mariana Mallard's. She was here this week, right? So I promised her that I would mention that and give her the credit for the joke. So Tarni, you keep on the cherry.
All right. So welcome back for the last talk of this morning. We have now a invited speaker, Evan, from University of Basel. He will talk for us about topological interlayer superconductivity in van der Waals heterostructure. Welcome.
Thank you. Thank you, Tarnier. Thank you to the organizers and Carlos for inviting me. Now just, this joke that Carlos made, there's actually more to that because I don't have many Norwegian friends in Switzerland where I work in Basel, but I have one. He lives in Zurich, and he is called Odd, which is also a very common Norwegian name. This is 100% true. When I tell this to physicists, they tend to not believe me, but it is. Maybe I should have had the picture of him. Okay, anyway. So I am working at the University of Basel, and the work that I'm presenting today was done in collaboration with these people. There's Joel Hutchinson, there's Jelena, and there's Daniel Loss. Okay, so just to give you some impression of where this is going, what we're doing is essentially we are proposing a setup where we can have something called topological interlayer superconductivity. So the idea is very simple. You have two TMDs, here and here. And by sandwiching some anti-ferromagnetic insulator in between, the idea is that now magnons in this anti-ferromagnetic insulator can mediate an effective interaction between electrons here in the upper layer and the lower layer and give rise to interlayer superconductivity where these essentially pair up. So initially the motivation of this work was to realize this interlayer superconductivity. And at some point a bit early in this project, me and Joel, so this is how it started, we had some discussion over coffee, and a bit later we had some disagreement. Joel said, I think we should try to look for interlayer superconductivity. And I said, well, I would prefer to look for topological superconductivity. And in the end I was kind of convinced by Joel, and they said, okay, fine, we will look for the interlayer superconductivity first, but of course I had my revenge when it turned out that in the results we actually found topological superconductivity almost without looking for it. Okay. So that's where we're heading, but I will need some time to build up until we get there. So in this conference, of course, we have already seen a lot this week. And I think something which I have seen many times is that in magnetism, if you have some, or condensed matter in general, you have some material, you can essentially modify the properties of this material by putting some other material next to it. And there's a lot of examples of this in this paper here, where I think at least one of the members in the audience here is an author. I just picked some different examples here. For instance, if you have a magnet, you put it next to some electronic system with large spin-orbit coupling. This will give rise to some DMI between spins in the magnetic insulator. And as Ivan showed us before the break, this can be important if you want to make topological magnons. Now, another example, which I kind of like, is this recent paper here on archive. So, of course, in this workshop, we already saw a lot of examples of hybridization between magnons and phonons. So here we have now some cavity, and you have some electric field and magnetic field inside this cavity. And I think for most of the examples that we saw, the magnons couple to the photons through the magnetic field. Because of course magnons, they couple to magnetic fields. But if you have now some AFMI here, and you put it next to some topological insulator, of course the electrons in the topological insulator, they couple to the electric field. While the spins of these electrons in this blue material here, they may couple to the spins of the antiferromagnetic insulator. So essentially, by considering this stack of an AFMI and a topological insulator, you can effectively mediate a coupling between the cavity photons and the magnons, which happens through now the electric field. Okay, another example. We already saw, or it was already discussed, that if you apply a magnetic field to some TMD, then you can get a splitting between the valleys. But this you can do also by putting your TMD next to some magnetic insulator. And often this will enhance the effect a lot. Okay, so you have in metal some material, you put some other material next to it with maybe some other degrees of freedom. This modifies the properties. Now, I always worked a lot on superconductivity, so a natural question for me to ask is, if you have a magnet, you put it next to the electronic system, can magnons in the magnet mediate superconductivity between electrons in the electronic material? Okay, and this is essentially what this talk is all about. Now, this has been investigated in several different papers, theoretical papers in this case, recently. Now I took some examples again. For instance, it was proposed that if you have a topological insulator, as we already heard, there are some edge states at the edge of this TI. Now they can couple to some ferromagnetic insulator, and this can now give rise to some very exotic type of superconductivity, where instead of pairing up an electron here with the one at -k over here, in fact, it could be what's called Amperian pairing, where you have electrons like this, sort of on the same side of the Fermi surface. So again, some proposal. We also had some hot topics session about altermagnets, and there's also this proposal here, where they consider some electrons hopping between the lattice sites here. You also have some localized spins in red here, and the idea is, again, the magnons in this system of localized spins can mediate an effective attraction between electrons hopping around here and give superconductivity. And finally, with Christina again, with Christina, that was yesterday, was it? We talked about some Skyrmian lattices. And in this paper, they look at whether magnons in Skyrmian lattices can also mediate superconductivity. Okay, so these were all theoretical proposals. Now, on the experimental side, the evidence is scarce, I have to say, and this is part of the reason that I go around and give this talk. It's in the hope that someone will, realize this experimentally and that we can see this magnon-mediated superconductivity. Now, there is one paper where they consider some nickel on this substrate here and then some bismuth on top. And they also consider some stack where they essentially remove the nickel. Now, nickel is magnetic. And what they see is that if you don't have the nickel there, then they don't find any superconductivity, at least not above this 50 millikelvin temperature. But then if they introduce the nickel, then suddenly they have superconductivity at 4 Kelvin. As you can see in this figure here, where you have the resistance as function of temperature, and there is a drop here around 4 Kelvin. Now, I don't find this work, they suggest that this is due to magnons. I don't find this work entirely convincing. Of course, clearly, it seems like there is superconductivity at 4 Kelvin, but the point is that it's not so clear whether this is due to magnons or not. Because when you put two materials next to each other, this can also you can have some diffusion of atoms into the other material and things like this, and this could introduce additional modes like phonons. So it's very difficult to kind of say something for sure about what the actual mechanism is. And my impression is that probably in this case it's not due to magnons, which is also why I think we should continue to look into proposals for where we can actually see magnon-mediated superconductivity. Okay, this was just putting it into some context. So for this talk, I will first introduce magnon-mediated superconductivity, and I will do this by discussing a paper of mine from a few years ago, where we see that if you have a metal or semi-metal between two antiferromagnetic insulators, we can find some D-wave pairing, and this is some kind of base case. And then we will move on to the topological interlayer pairing when we have an understanding of how magnon-mediated superconductivity works. Okay, and I like to start from the very basics. Now, of course, this is a conference on magnonics, primarily, not on superconductivity, so I think this is a nice place to start. Now, Poliana already gave a talk on superconductivity, and you said that it wasn't really connected to magnons. I guess what I'm trying to do here is to provide some link, how to connect magnons with topological superconductivity. Anyway, okay, so superconductors, of course, they have no resistance. That's where they get their name from. But the more important property is that you have the Meissner effect, perfect diamagnetism. So in this pictures here, you can see some magnets, which is levitating on top of some superconductor. Both here, in this very old picture, it's actually a video from 1965. And this, which is the standard picture of a superconductor, which is one of the first hits you get on Google. Okay, but now, the question for you is, what is the difference between these two pictures? Yes? So, okay, so you can do both, right? You can have a magnet levitating on top of a superconductor, or you can have a superconductor levitating on top of a magnet, which is what they do in the trains. So it's a good guess, but no, that's not what I am thinking about. In both cases, this is the superconductor, and this is the magnet. So not quite. The temperature, yes, the temperature is different. So which one do you think is lower or higher? This one has a lower temperature, yes. It's much lower. So what do you think the temperature is here? 4K, yes, correct. 4K, it's cooled by liquid helium. So how about this one? Yes, it's cooled not by liquid helium, it's cooled by liquid nitrogen. So why is it that we need to use such much lower temperatures here than we do here? It's because these are different types of superconductors. In particular, this is a type 1 superconductor. This bowl here, it's the one down here, lead. And you see that this is some bowl shape. Because if you put the magnet on top of this bowl, it will kind of float around. It will be repelled from the bowl, but it's not stable. Now, if you were to do the same on the second picture here, the levitation happens through something called the flux spinning effect. So the magnetic field can partially go through this superconductor. And because of impurities in the superconductor, basically the magnet will stay fixed at exactly the same position. So if I did have the videos, you would see that there is some difference. And okay, so since you don't have this flux spinning here, you essentially need this bowl to ensure that it just doesn't fall off. Yeah.
It means that the first one you can easily move. The second one, you need to push some.
Yes, exactly. It's like a harmonic oscillator, in fact. If you try to push it to the side, it will start oscillating. And then it will relax. Okay, so this one was lead. It's one of these green ones, which are called the conventional superconductors. And these we understand very, very well. This is what essentially we have understood since BCS came up with their theory in the 50s. And there was in fact a lead. This paper, this picture is from 1965. 1965, the only superconductors we knew were the conventional ones. But then, 1995 roughly, we also discovered new classes of superconductors, these cuprate superconductors, which have a much higher critical temperature. And these are much harder to understand. And of course, there have been big fights about what the mechanism is of superconductivity in these materials. And it's not quite settled. My feeling is that it has to do with spin fluctuations. And I think that spin fluctuations is involved is fairly well established at this point, although I have some colleagues which claims that phonons can explain all of it. So, you know, we have fun at lunch. Okay, another class is actually these heavy fermion materials in the light green. And they have actually quite low critical temperatures, but I also think that, or it's pretty clear, I think that spin fluctuations also have something to do with this. Okay, and I should mention already now that these light blue ones, they are typically D-wave superconductors. There are many things we don't know about these cuprits, but this is something which we know very well. Okay, so the basic mechanism of spin fluctuations mediated superconductivity is very simple. In phonons mediated superconductivity, you have an incoming electron scatters off a phonon, and then the phonon is absorbed by some other electron. And for the spin excitations, it's very similar. You have some incoming electron, which transfers its momentum and also spin to some localized spins, for instance, in this case. And then, of course, this one propagates, another electron comes in, and this spin flips as well. And then one of the primary differences is here, the spin stays the same in the scattering processes, and here it switches. And this is now a simple picture for how superconductivity can appear, probably in these Kondo lattices, which are related to the heavy fermion materials, or also in the theoretical description or the theoretical model, the Hubbard model, which is believed to have something to do with the Kupert superconductors. But the system that I want to focus on is this one, where you have some heterostructure with some electronic system, some magnet, and then you have electrons interacting through magnetic excitations in the magnetic system, which is now a magnetic insulator. Okay, yes, and of course, as physicists, theoretical physicists, we like to describe this by Feynman diagrams. Okay, so now let me get to this paper that I already mentioned, this one here, where we consider the system. And we consider some antiferromagnetic insulator described by this Heisenberg model. We have some normal metal system described by some hopping model like this. And we have some coupling between the spins of the electrons and the spins in the antiferromagnetic insulators. And I would like to point out already now that I have introduced some JA bar, which describes the coupling between this side and a spin on the B sublattice of the antiferromagnet. And this one can in general be different from this coupling. And while this may seem a bit artificial, the idea we have in mind is that if you have an uncompensated interface, basically the normal metal will couple much more strongly to one of the sublattices, while if you have compensated interfaces, it will probably be the same. Okay, so this is the model. Now let's see if we can get magnon mediated superconductivity in here. And the way that we do this is we just go through some list of steps. First, we diagonalize this electronic Hamiltonian by doing the Fourier transformation. And from this, we can find what the Fermi surface looks like. Then, as Sylvia taught us in the tutorial, we take the antiferromagnetic Hamiltonian, we introduce the Holstein-Primakov transformation, write it in terms of magnons, and then you can diagonalize this one through a Bogoliubov transformation, and then you introduce the Holstein-Primakov also in this term here. Next step is you derive some effective interaction between electrons here, mediated by the magnons. And we do this using some, you can do it either using a Schrieffer-Wolff transformation or some field theoretic S-matrix expansion. And then you can derive some gap equation, and then finally you solve this gap equation. Okay, so this is what we will be doing next. So let's just look into this in a little bit more detail. Okay, yeah.
So before you go into the details, so the electron-electron interaction, the ordinary one, right?
Yeah. Mm-hmm.
I'm just thinking of the ordinary superconductivity where we need
Yes.
phonons to overcome the electron-electron interaction.
Yeah.
will we consider something like that in the end? That there is going to be a competition, and you're going to show that the magnums will somehow overcome the positive.
So I will not
interaction?
consider the electron-electron interaction explicitly. What I can say is that essentially the fact that we consider spins and spin fluctuation mediated superconductivity means that you will get superconductivity in a channel which is not the standard spin singlet S-wave channel. So spin singlet S-wave, that's typically very strongly suppressed by Coulomb, but you don't have the same problem when you consider P-wave, D-wave superconductivity, which is what we will eventually get. So in principle, I mean, we should consider it, but we expect it to be much less relevant in our case than if you had phonons. Okay, so, yeah.
We have a second question, if you allow.
Yes.
Quick question. What's the need for the two magnets?
What's the need for the two magnets? Okay, so remember we had, let's go back to the model. Remember we have two different J's here. Now, if these are the same, I would say there is no need for the two magnets. But we also want to consider the situation where you, for instance, switch this one completely off. And if you do this, this magnet here will now give rise to a net magnetic field. And that's not good for superconductivity. So by going to the situation where you have two magnets, you can switch off this JB coupling without having a net magnetic field. And this is then much more favorable for superconductivity. So it's essentially to be able to explore the whole phase space of having different ratios of these JAs and JBs. Okay. Back here. Yes, introduce Holstein-Primakov and effective excitations, which are spin flips on the A and the B sublattice. This gives us this Hamiltonian, which can be diagonalized by a Bogoliubov transformation. And then we can find the Magnon spectrum. Now, what I will point out is that these coefficients UQ and VQ, they do not satisfy a unitary constraint. They have a minus in between. So what this means is that if there was a plus, essentially the size of each one of these U and the V would be constrained, right? It couldn't be larger than 1. Here, in fact, UQ can be much larger than 1. So effectively, this alpha Q can couple strongly to the electrons, if this is indeed the case. And this is something that we will be exploiting. So one simple way of understanding this is that essentially, if this is the case, that this UQ is big, the Magnon excitations that we have are not simply a spin flip on sublattice A, but it's a superposition of one spin flip on A and 2 on A, 1 on B, and so on. And essentially, this is now some sum which has significant weight even for these terms with a large number of spin flips. And if you now couple only to a sublattice, for instance, effectively you couple to some large spin. And this again is some other way of saying that you enhance the interaction by being in the situation where UQ is large, which corresponds to having a weak anisotropy. Okay, I will make one more point before we can go into what kind of superconducting order we have. So in the model that we have some normal metal with some lattice, and the periodicity of the antiferromagnetic insulator is different because we have antiferromagnetic order. So essentially the Brillouin zone of the magnons is smaller than the Brillouin zone of the electrons. Okay, so there's now two kinds of electronic scattering processes. If I have some electron on the Fermi surface, it can scatter with a small electron inside this red square, which is what we call a regular process, or it can scatter with an additional momentum vector q to some point inside this blue region. Okay, and the question is now, which of these processes are the most important? Is it the small momentum scattering processes or the large momentum scattering processes? So to do this, we introduce some Magnon propagator, which looks like this. So we have some coupling between the electrons and the magnons, and we now kind of absorb this into a prefactor in front. Okay. And now there's two cases. There's the case where I couple to only one sublattice, and then if I take some electron here and I scatter it through some magnon to this point here on the Fermi surface, characterized by some angle theta, then this figure here shows me what this A of Q is. So in the case that I only couple to one sublattice, you see I have this black curve, and the most important processes are the small angle scattering processes. But now, if I couple equally to both of the sublattices, it changes completely. And now the small angle scattering processes are suppressed, and I have peaks for these umklapp scattering processes. Yeah.
So why are you considering the green circle? Kind of is the Fermi.
Yes. So now we imagine we have some chemical potential and we have some Fermi surface here. Yes.
Will it matter whether you're going to be at half filling, whatever that means in this case, or not?
Yes.
For nesting at some point.
Exactly. So if we have nesting, then essentially the vertex corrections will be important. And then it's kind of hard to say what we will get within this weak coupling framework. So we are trying to stay a little bit away from the perfectly nested case because we can't really trust the methodology that we're using when we're close to this point.
But usually when you have nesting, that's when things really happen, right?
Yes.
The instabilities and
yes.
all that.
So it's kind of a balance, right? We're kind of going towards that limit because we know that this will typically enhance our pairing. But then again, we're careful to say something too strong about exactly that point where you have very strong nesting.
Maybe I don't understand quite, but you called this an umklapp-like process, but
yes.
It looks like theta is pi/2 at the peak. So is it really a reciprocal lattice vector that connects the 2 points, or is it some fraction of a reciprocal lattice vector?
I'm not sure I quite understood the question, but why I call it the umklapp scattering process is
yeah, the picture suggests that it's a reciprocal lattice vector, but then the next picture, maybe the peak in the green curve, maybe I just misread the diagram. Is it theta equals pi/2?
So if you scatter by here, this is pi by, I mean, the peak, it corresponds roughly to from here to here.
Oh,
right?
okay. Sorry. Yeah, no, it's fine.
So the color here in the background kind of just mimics.
Yeah,
you know,
I thought it was half
regime.
a reciprocal lattice vector, but it looks good. Okay, thank you.
Okay, so we can also understand this as some sort of interference between the sublattices. So essentially, when you turn off this omega b, you have only uq squared plus vq squared, whereas if you have both of them, you have uq plus vq, and then this can either be it can add up to something big if you have this one to be positive and this one to be positive, or it cancels out if this one is negative and this one is positive, which is exactly what's going on down here. Okay, but the main point of this slide is we have different kinds of processes which are important depending on how we couple. So if we couple to one sublattice, the small momentum scattering processes are the most important. If you couple to both, the scattering processes with momentum vector q are the most important ones. Okay, and this is now how we will understand the superconducting pairing. This is a gap equation. So here we have now some anomalous correlation function, and we can write down some S-matrix expansion for this one. This is what I call the sunset diagram, which is typically the one which gives you superconductivity, also with phonons. But the difference from phonons is you have some C dagger, both with spin up. At the vertex, because magnons carry a spin, the spin flips. And then at the second vertex, the spin flips again. Okay, so this is now the up-down anomalous Green's function. I can also write down the corresponding diagram for the down-up Green's function. And then I can make spin singlet and spin triplet combinations, right? So this gives me now essentially the gap equation. I have the spin singlet, so this is up, down, minus, down, up, and up, down, down, up. And the important thing is that because I have the spin flip at these vertices, I have a minus sign in front here. And if I considered phonons, it would be plus. Because essentially, if I flip the spins here, this minus sign goes over here. And this means that while for phonons you have S-wave superconductivity, spin singlet, when you consider magnons, that channel will be repulsive. So the question is, what will you get instead? And the answer is you can compensate this additional minus sign by considering a D-wave profile. If you scatter an electron from here to here, the fact that the gap has a different phase here and here will compensate this minus. And we know that these scattering processes here are important when you couple equally to both sublattices. Okay, so if you couple equally to both sublattices, we expect D-wave pairing. While if we couple to only one sublattice, these small momentum scattering processes are the important ones, then we cannot get S-wave, spin singlet, but we can get equal spin-spin triplet pairing. Okay, and I will now show you the phase diagram that we find. So what we have on the axis here is omega, which is the ratio of these two. So here we couple to one sublattice, here we couple equally to both. And what I told you was if you couple to only one, you get some spin triplet pairing, either this P wave or the F wave pairing, whereas if you couple equally to both, you get D wave when we are close to half filling, as Carlos mentioned. Because basically, you need to have a sizable Fermi surface to be able to to be able to get close to this momentum scattering process by Q. Okay, so the important takeaway messages from this first part is, first of all, magnons carry a spin, and this affects which kind of superconducting pairing you can get. In particular, you cannot get spin singlet S-wave pairing, which is what we get from phonons. And I showed you that, okay, depending on exactly what the model looks like and how you couple to the sublattices of the antiferromagnet, you can get D-wave pairing. Okay, so now things are going to get even more interesting when we ask in the second part the question of whether you can get more exotic pairing. Are there any questions at this point? Yeah.
So you choose, you're actually doing the calculations, right? But you just showed, can you go one slide back?
Yeah.
So this is the result of the calculation, right? So you're predicting you can have P, F, or D type pairing by varying the ratio. So what controls what the symmetry of the other parameter is, for instance, the ratio.
Yeah.
Is that the message here? That you can tune whatever kind of superconductivity you want?
So I think in practice, tuning this parameter is going to be difficult. So, if you actually want to, if you're a theorist, it's very simple.
Sure, no, I'm
that's
a theorist.
That's the picture you should have in mind. And if you want to do experiments, probably you need to choose how to cut your magnet. And if you cut it in such a way that the interface is compensated, you will be somewhere over here. If you cut it in an uncompensated way, it will be somewhere here.
Mm-hmm.
So I don't think you can go back and forth here, but by how you cut, you can decide kind of roughly where you want to be.
And this is the gap equation, you're actually solving it self-consistently?
Yes.
Okay. Mm-hmm. Thank you.
So I guess you're kind of close to the nesting condition, right?
Yes.
So in principle, should you be considering possibility of other instability channels at the same time and kind of show that Cooper's instability is probably the dominant one compared to let's say other ones like SDW or?
Yeah.
other types of instabilities.
Very good point. So we do expect other instabilities as well, and this is not part of this work, but it's something which I'm looking into right now. So based on the results we have so far, it looks like if you have weak interaction between electrons and magnons, then the dominant pairing channel will be superconductivity, D-wave superconductivity. And if you go to very, very strong coupling, probably beyond what's reasonable in an experiment, then you can have coexistence of spin density wave, out of plane spin density wave to be more precise, and superconductivity. So I've been looking into this recently, but yeah, not here.
I do have a question myself. Is every time I think on superconductivity and magnet, I come into mind the FFLO type of coupling with a finite momentum.
Yeah.
Should I expect the same here because we have magnet, or how?
Okay, so first of all, in this work, we only consider zero momentum pairing. FFLO pairing typically occurs because you have some magnetic field, right? So in this model, there is no magnetic field which splits the Fermi surfaces in such a way that FFLO is probably the most relevant one. So in this model, no. In the model with only one magnet, basically, and an effective magnetic field, which So was asking about, maybe this would be relevant. But so FFLO pairing typically has a smaller phase space for scattering, right? So this is the reason that FFLO is typically less relevant than zero momentum pairing. So when you add FFLO, then often, it will be less relevant because of that. Okay, I will move on to this next part, which is about this work. Okay, and the motivation for this work was, first of all, we wanted to go in the direction of finding something topological. This was the motivation, one motivation. Another one was we wanted to realize the interlayer pairing between electrons in this upper and the lower TMD. So first of all, we had a talk by Poliana earlier this week, and one of the sort of simple systems where you can have topological superconductivity is if you have a nanowire and you subject it to, you put it next to some superconductor, and this superconductor is now just standard spin singlet S-wave superconductor, which is not topological. But if you have spin orbit coupling with some vector alpha here, and you have a magnetic field here, typically you can kind of transform the trivial superconductivity up here into some topological superconductivity. And the idea is that then you will have some Majorana edge modes on the sides here. And the hope is that you can now use these to do topological quantum computation. So these Majorana modes, they are essentially anyons. So if you interchange them, you will have a phase. And somehow you can use this for topological quantum computation. Now, a few months back, Microsoft made a big announcement, had a big press release, where they said that we have made a chip containing, and they called it Majorana 1, very fancy name, and they say that this one has topological qubits. Okay, and this attracted a lot of attention also on the March meeting. Please, no pictures, Carlos, I don't want to get sued. Okay, too late then. Okay, so yeah, I will be more careful than certain of my colleagues who have been among the ones who have been criticizing this work. So I think the community hasn't really recognized yet that this is kind of indeed what Microsoft claims that it is, but I'm not into the details in sufficient. Yeah, I don't know the details well enough to say anything conclusively. I will just say the community doesn't agree exactly about what these results show yet. So for me, this means there is still plenty of room to look for topological superconductivity in other systems. And we heard already that spin orbit coupling is a very important ingredient to get topological superconductivity. One system which has strong spin-orbit coupling, which we already talked about, was the TMDs. So they consist typically of some M and some X atoms, which can be molybdenum or tungsten, and X, which can be one of these three. And typically they have some structure like this, as we have already seen. And now from the symmetries of this system, actually inversion is broken. Yeah.
The TMD
Yeah.
must be hexagonal, or can we have a different configuration?
I don't. So the TMDs that we consider have this lattice structure here, but and that's most TMDs, I guess. So I'm not aware of any example which does not have this lattice structure, but I won't say for sure that it doesn't exist. Okay, so this one here, it breaks inversion symmetry. So basically it means that you do not have some two states at this point, this K, where you have both spin up and spin down. So instead, since you have strong easing spin-orbit coupling, that's what this is called, you have a state at K with spin up and a state at minus K with spin down, and this follows from the symmetries of the TMD. So the spectrum, if you hold up it, looks like this. You have K and you have K prime, and then you have parabolic bands like this with opposite spin. And I should also say that in this whole doped regime, the orbitals are primarily localized close to the M atoms in the TMDs. So essentially you have electronic states on some sort of triangular lattice. Okay, so this is step one. We introduce some spin-orbit coupled electronic system. Now another motivation we had was the following. So you know that superconductors, they can act as sources of correlated electrons. So if you have a Cooper pair and you have a so-called crossed-on wave reflection process where you have one spin up and one spin down, like this, and they split up and they tunnel into different qubits, then the spins here and here will be entangled. But you can also have other processes in a system like this, for instance, this one here, direct and wave reflection and elastic co-tunneling, which does not give you correlated electron spins in the same way. Okay, so the idea we had, okay, and this was also, this experiment here is one experiment where they actually show this. You have electrons in the superconductor, and you have crossed-on wave reflection processes where the Cooper pair splits up and tunnels into these two quantum dots. Okay, so the idea we had was...
Excuse me.
Yeah.
Sorry, what is the what is the number?
This one here.
Yes, please.
Okay, this is essentially it quantifies the degree of entanglement between the electrons in this experiment. Okay. And if it was -1, that would be perfect. This one is minus 0.37. Okay, our idea was you have two TMDs, and if we put an insulator in between, then electrons cannot tunnel from here to here, and so elastic co-tunneling processes are suppressed. And basically this leaves us with only crossed-on wave reflection processes if we can somehow pair up electrons across this layer. Okay, so the question we asked now was, how can you somehow realize this interlayer pairing? So we needed to ask the question of how should we somehow, what kind of system should we have up here? What should we do to our TMD? What kind of insulator should we have between? And then once we have kind of settled down on model, what are the properties of the superconductivity? Okay, so let's start thinking about this. If we have a TMD here, then we now have A up close to the K point, and we have A down close to the K prime point. And then since we have two TMDs, we have double up, right? So we have also some B bands. And now the problem is that if you want to make Cooper pairs with zero momentum, you can have an electron here and an electron here. But there's two ways to make a pair now. Either you make an intralayer pair, which is not the one we're interested in, or you make an interlayer pair. And this is possible because the spectra satisfy these symmetry relations. So the question to you is now, how do we make sure that this one comes out as the winner? Well, the easiest way to do it is to break this symmetry while retaining this symmetry. So what if we instead had Fermi surfaces looking like this? Then the zero momentum pairs would be an electron here with an electron here. And this we can do if we kind of make this Fermi surface A up bigger and the Fermi surface A down smaller, which you can do by an effective Zeeman field. And how do we make an effective Zeeman field? Well, one way to do this is to couple the system to a magnet. But we have also the B layer, right? We have B down and we have B up. And this one we want to shift in the opposite way. So the model that we propose looks like this. You have the TMD here, and the lower layer couples more strongly to the down spins of the antiferromagnetic insulator, while for this upper TMD, you couple more strongly to the up sublattice of the antiferromagnetic insulator. And fortunately for us, you can now, as I like to call it, kill two birds with one antiferromagnetic insulator. First of all, you get the right Zeeman shift that we want for interlayer pairing. Second of all, and this now remains to be seen, this antiferromagnetic insulator hosts magnetic fluctuations, which we hope can mediate superconductivity. Okay, so, yeah.
And in this case, having only one layer magnetic is not a problem.
You mean the fact that we only have one AFMI?
Yeah, exactly.
No, that's not the problem, no. Okay, so now let's write down the model for this system. Again, it's the same type of model. You have an electronic Hamiltonian with some spin-dependent matrix elements here, which we need, of course, to have some coupling between the momentum of the spin. You have some antiferromagnetic insulator and some coupling between electron spins and the spins of localized, localized spins. And, okay, now let's go through, so before we continue, what kind of materials could this be? We looked through a long list of possibilities. We have already seen this figure here. And it was actually kind of hard to find some material which fits all our requirements. We came up with kind of two solutions. The first one is the one I've already shown you. If there is some lattice matching between the TMDs and the antiferromagnetic insulator, then essentially we have the situation that you already have here. The electrons are primarily localized close to these blue atoms here, therefore couple more strongly to the up sublattice. And this kind of stack with now the candidate that we found, manganese phosphorus triselenide, has been realized experimentally, which is good for us. And they looked into some excitons in this system. Okay, so this one has a nice experimental precedent. Now the lattice mismatch of the antiferromagnetic insulator and the TMD was about 2.6%, so it's not perfect, but at least I think we can expect some reasonably big domains. Okay. Now the second option, which is probably more appealing, is you considered a layered antiferromagnetic insulator. So essentially, for instance, you have this manganese bismuth telluride, where essentially the upper layer here has spins up, and then the next layer has spin down. And if you now have a bilayer of this, say, then essentially naturally, just by sort of the set component here, the up spins will couple more naturally to the upper TMD, and the down spins more naturally to the down TMD. Okay. So, if any of you have a lot of experience with these materials, I hope we can discuss and that you may think about constructing these kinds of stacks. Okay, now let's continue. Again, same procedure for deriving the effective interaction, deriving the gap equation, and solving the gap equation. Yes?
I think we have a question.
Yeah.
Is need the only antiferromagnetic isolators possible use metal antiferromagnetic of this layer?
I think that would be possible as well. But so, you know, we did this calculation and this theory for antiferromagnetic insulators. So I wouldn't be able to say with a lot of confidence that it works in exactly the same way. But I think in principle, I don't see why that shouldn't be possible either.
Yeah, because it's more easy to calculate the antiferromagnetic is a laser.
Okay.
Yeah. But it's not experimental realization use a metal antiferromagnetic.
What do you mean if it already exists?
No experimental realization.
No, not of this, not yet, no.
Okay.
Okay.
Sorry.
Yeah.
There is a second question over there.
But if you, I was thinking that the insulator was needed because then you have charge transfer with band alignment, and this effect would not be spin selected. So
yeah, I mean, it's a very good point, and which is one of the reasons that you expect things to change qualitatively if you do not have a magnetic insulator. But you know,
okay, and
any kind of degree of freedom could, in principle, give rise to superconductivity if you just have strong enough fluctuations. But of course, you know, you need to look into the details then.
And my other question is the thickness of the antiferro insulator considered? Because the interlayer of the TMDs are not coupled very well. And if increase with the two layers other than the other possibility, this is included?
Yeah, it's a good point. I mean, it doesn't, so it's good for us to have a thin antiferromagnetic insulator, because otherwise, as you pointed out, the coupling will be too weak.
Okay, thank you.
Okay, so this is the program now. Let's go through it in somewhat detail. We have already talked about the electronic spectrum. We take this Hamiltonian, this gives the spectrum, and we take the 0th order term from here. This gives us this spin and layer dependent splitting, which we already talked about. Now for the magnodes, exactly the same as before, exactly the same type of Hamiltonian. And I will point out that this quantity dq here, it couples, it appears in front of this aq, bq type of term. Now when you diagonalize the spectrum, you get this, and we have plotted the spectrum here. And I should also say CQ is given by this constant here in our calculation, and DQ is given by this one here. And this quantity here, we know it from graphene. It vanishes at the K and the K prime points. And if you sit close to the K point, it has some phase. And as you move around, the phase winds. Okay, and this will be important. And the reason that I'm pointing this DQ out is it appears very prominently in our gap equation. Now, a little bit for the experts. The magnon spectrum is modified by coupling to the electrons, and we take this into account as well. So this is our bare magnon propagator, where we define some spinors phi q down and phi q up. Because they have two operators in here, this is now a 2x2 matrix. Now, if we consider renormalization by the polarization bubble, this polarization here, which is given by some Lindard function expression, enters on the diagonals here. And it changes our spectrum from this to this. And then, you know, this is the result with the yellow and the purple curve here for the renormalized spectrum. And essentially, what it does is it pushes the spectrum down close to K and K prime. This turns out to be good because small magnon frequencies is good for superconductivity. Okay, next we derive the effective potential. So we start out with now the first order terms from here. And these can be written like this in terms of the magnon operators. And this we can also think of pictorially in terms of these interaction matrix elements. And now, which ones of these can I combine to give rise to an effective electron-electron interaction? What do you think? Let's start with one. which ones can I combine with 1? What did you say? 2. Yes, I can combine 2 with 1. Good. This gives me an A dagger propagator. And it gives me an interaction between electrons in A and A. So it's correct, but it's not the one we're interested in, because essentially it doesn't have the large phase space for scattering that we want, and which follows from how the Fermi surfaces looks like. So if it was only that possibility, there wouldn't be any interlayer pairing. So there is one more. So where is the other one? Okay, well, there's only 2 options now, right? So 3 or 4, which one do you think?
I'll say 4.
4. Okay, excellent. 4. So 4 has now incoming A up, incoming B up, and it scatters to B down and A down. But now let's think about conservation of spin, because my model conserves spin. So this one is not good either. So this leaves us with 3. This is the one we should combine with this one. And if we look back at the Hamiltonian here, this is exactly the kind of term that we have, right? We can combine A with A dagger, that's this one, and we can combine A with B. And this gives us now A up, and B down goes to A down and B up. Okay. And this is the one that we hope will give us topological interlay superconductivity. So this is the diagram that we're after, and it corresponds to this expression. And the effective potential that we get here after we do a Schrieffer-Wolff is given by this expression here. And it has this D in it precisely because we have the A to B propagator. And the picture is this one here. You have an incoming up spin electron, scatters to spin down. And then you have a magnon propagating here, corresponding to this factor. And then another interaction with an electron down here. So based on this picture, essentially, we can just derive pictorially this effective interaction. Okay, now we derive a gap equation. And it looks like this. It describes scattering of an electron here to an electron here, right? 5, yeah. Okay, so you have an electron here and an electron here. They form a Cooper pair. Now these Cooper pairs scatter from A up here to A down here, and from B down here to B up here. So because of this, our gap equation, which now describes pairing amplitudes on A up Fermi surface and A down Fermi surface, has elements on the off diagonal here, because this couples A up to A down. Okay? And the effective potential is this W. And now we can plot this effective potential in the complex plane. So what we do is we consider this theta prime to be fixed. And then we have this theta here, and we just vary it. We let it run around the Fermi surface here. And this gives us this yellow curve, right? As we change the position of this gray dot, you get some curve in the complex plane, which corresponds to this yellow curve. And then you can do the same for the inner to outer scattering processes, where you start out on the inner Fermi surface and you scatter to the outer Fermi surface. And this gives us the purple curve. Now again, can you tell me the big difference between these two curves? Yes, exactly. One finds the origin and the other one doesn't. And this is now important for the topological superconductivity. So what we do now is we solve this gap equation, and now comes the result. The result looks like this. So this now is the superconducting gap on a Fermi surface. So this is delta A down, for instance. This is delta A up. And the height here denotes the magnitude of the gap. And the color here denotes the phase. So on the inner Fermi surface, you see we have a constant color, orange. And here we have a blue, which corresponds to the opposite sign. So here, this is now sort of, if you sit locally at K, at least this looks like some sort of S-wave pairing. That's topologically trivial. But then for the outer Fermi surface, you have a phase winding. So essentially you just move around here on this phase. So this is topological p-wave pairing, px plus ipy if you wish, and you measure relative to this point. And okay, we have some BCS-like curves here as well, where you show that essentially you have some value at 0 temperature and then it goes down at the critical temperature. So chiral p-wave pairing indicates topological superconductivity. And we will see that that is indeed the case. First of all, first I will comment on the critical temperature. So since this is essentially some weak coupling theory, we get a weak coupling result. So some standard formula here for the critical temperature. And this formula here relates this effective coupling strength to our various system parameters. So for instance, you see that you should have strong interfacial coupling. As we already mentioned, you should have large spin, and the Magnon frequency should be small. And then we make some estimates for what the critical temperature can be based on our materials for this manganese phosphorus triselenide and this MBT. Now one parameter which is very,
So you mentioned the topology.
Yeah.
What kind of topological state are we talking about here? Is this a Majorana at some point? You're going to use this?
So I will get to that very shortly, I think. So let's just postpone for, yes, for 1 minute, exactly. Okay, one parameter which we do not understand, or which is very hard to both measure and calculate, is this J bar, which is the coupling between the localized spins and the electrons. So we were kind of forced, I mean, we looked through the literature a lot, couldn't really find any reliable values for it for these stacks, and the values vary a lot for when we consider other different stacks. So in the end, we just plotted it as function of J bar. And okay, we see that if J bar is quite strong, then we can get to some Kelvin range temperatures. But this, I mean, finding some reliable value for this one, that's kind of a next major step if we want to realize this stack, I think. And now, Carlos, we get to the topological edge states. So we can write down the Bogoliub of the Jens Hamiltonian with this kind of pairing. It takes this very nice block diagonal form. So essentially, for instance, this one forms a block with these ones. So we have 4 different blocks. 2 of them have this chiral p-wave pairing. 2 of them have trivial s-wave pairing. And you can calculate Chern numbers. We have seen the formula earlier today. Okay, so we find that, oh, I mixed up the C's here. This one was supposed to be 1, and this one's supposed to be 1, and this one was supposed to be 0, and 0 here. Okay, so the topological blocks now give us this Chern number. Okay, then we can put it on a finite lattice, and you can calculate the spectrum, and we see that we indeed have these topological Majorana edge modes crossing the gap for the topological blocks, while this orange one, which is topologically trivial, does not have any such edge modes. Okay. And now, I think one very nice thing about this proposal that we have is that the Chern number corresponds to essentially the direction of magnetization in our magnet. So you can kind of just look at the magnet and it will tell you what the Chern number is in some sense. So if you have some domains, for instance, this could give you edge states in the topological superconductivity depending on what the magnetization is on either side of the domain. Okay. This brings me already to my conclusion. I will leave it here. What we essentially showed is you can have this topological interlayer superconductivity by making a stack of TMDs and an antiferromagnetic insulator in between, which fulfills 2 roles. It gives us the right kind of Fermi surfaces to favor interlayer pairing, and it can provide the fluctuations which act as pairing glue to give us superconductivity. Okay, thank you.
Thank you, Evan. I think we can have 1 or 2 more questions. We already asked some, but I see some.
So this pairing that you get with so the say A dagger, B dagger, right? So this was the kind of pairing that you get, right?
You mean this one
yeah,
here?
A dagger, B
Yeah.
dagger, or
Yeah,
A, B.
or yeah, the way.
So
Okay, so
this
this is just the magnon propagator, right? Which from A to B.
Yeah, but I could also understand it as some kind of two-mode squeezing term, right?
Two-mode squeezing.
For the magnons.
So okay, it depends a bit what you mean by squeezing, I think. So when I think about squeezing, I think about the ground state of the antiferromagnet or something like this, and I say that the ground state is squeezed. And this comes essentially from this term in the Hamiltonian.
Yes.
But I would say in this case we have some virtual magnon, or kind of the creation of two magnons on the two sublattices, and this gives us the pairing. And if you want to call that squeezed, yeah, that's probably reasonable.
So okay, maybe two questions. Is there? So you showed one way of understanding why this, but I was just wondering if there is some intuitive way of thinking why exactly this term and not. So without diagrams,
I see.
And the other.
So you mean why this one gives me interlayer pairing?
Or why is there the relevant coupling? Yes, that you.
Yeah. Okay. So the way I think about is, so you have this upper layer here, right? It couples to the A sublattice of the antiferromagnet, and the magnon needs to propagate from A to B before this B sublattice can interact with electrons down here.
Oh.
So it is the A to B propagation of the magnet which gives me the interlayer coupling. And the A to B propagation is described by this term here, and that's why I get the DQ.
Okay, and related questions. So if you would now suppose that you can create a state in which you have these pairs, so you have a finite expectation of these pairs, will this enhance the effect?
Well, first of all, in the ground state, you do have a finite expectation of this quantity, don't you?
Okay, but say that I drive.
So basically, if you calculate the expectation number of AQ, A dagger A, here you get the finite expectation value for the antiferromagnet, right? And it's basically because this one appears in the Hamiltonian. Okay, not exactly.
I'm just thinking in an expectation value of the group pairs,
yes,
right?
of this one.
Yes.
But I think you will also get the finite expectation value for this one, right? Let's go back to the Bogoliubov transformation. Okay, so AQ is related to alpha and beta dagger, and BQ is related to beta and alpha dagger, right? I guess we need the inverse one from this one. So if you take the expectation value of A with B, I would expect to get the finite value in the ground state of the antiferromagnet.
Okay, yeah.
Right, we do have questions. We do. I think there are some people online. Okay, please go ahead.
Hopefully it's quick. So I think I missed the whole argument about why it is that you have suppressed intra-layer pairing, which is also in principle allowed.
Okay.
So what is the reason that the intra-layer pairing is subdominant relative to the interlayer pairing? I understood that the interlayer pairing exists, but the question is why is it?
So the interaction term exists. The interaction term exists, for sure. But it's also about kind of the fermionic energies, right? So if you have this pair here, you can scatter this one to here and this one to here. And no matter where you scatter this one, I mean, you will always get to the Fermi surface when you move this one by minus the same momentum, right? But if you instead consider this one and this one, if you scatter from here to here, this one will go off Fermi surface. So the effective pairing amplitude will be suppressed from the electronic energies in this process.
Okay, I see. I think I understand. Thank you.
Okay, so now I'm kind of thinking, let's say experimentally we're going to realize this, there's going to be some disorder in the metal, right?
Yes.
And for intrinsic P wave, it's very fragile to disorder.
Yeah.
But I'm wondering, is there understanding on how this is proximity-induced superconductivity? So I don't think it's the same as intrinsic P wave. It's extrinsically induced. So do people know like the fragility of this extrinsically induced P wave to disorder?
So first of all, I don't really agree that this is extrinsic P wave. This is still intrinsic because you have magnons which mediate some sort of interaction, right?
Okay, so then it will be fragile.
So I think
so it will be
will
fragile
probably
to disorder.
be fragile, yes.
Okay.
But okay, the TMDs, I'm not an expert on disorder, but I would expect that TMDs have sort of low disorder, right? But okay, maybe someone else knows.
Actually, this was part of my question.
Yeah. Okay. Yeah.
The role of disorder. I actually didn't understand, but because So just mentioned proximity induced.
Yeah.
The question is Anderson's theorem valid here to protect, this fragility?
Well, so Anderson's theorem, as far as I understood, requires S-wave pairing, right? Is that correct? Yeah. So, I mean, here you kind of have both S-wave and P-wave pairing, right? But since you have a P-wave component, I would expect, and I agree with So, I think, then that this one is more fragile to disorder than S-wave pairing. And then I can't really quantify exactly how fragile this is.
All right. I know we all want to stop because we're over time, but I myself want to ask you one last question before we go. Is the interlayer situation remind me of the normal topological superconductor where you have superconductor interlayer with a topological insulator. And the question I have is that gives you an effective topological superconductor in that model.
Okay, so once more, the model was?
It's just a regular superconductor
S-wave
interlayered with topological insulator.
Yeah.
So you do it many layers.
Yeah.
The final model that you have is a topological superconductor.
Okay. Yeah.
And why should I pursue this? That seems more complicated against that. What kind of advantages should I expect to use magnons instead of
Yeah, it's a very good question. So I think, this is intrinsic superconductivity, right? So I think that's at least some pronounced difference from the kind of taking the S-wave superconducting properties and modifying them. So I think there might be some advantages to that, but I don't know exactly, to be honest, precisely what those advantages would be.
It was a teasing question. I already knew it. Right.
And since we still have time, still have 20 minutes before lunch. So and we just ate, right? So, have you looked at, say, bound states? Topological, whatever. Like Majorana
so
bound
you mean like, assuming you have some vortex or something like this, and then we haven't looked into it in detail, no. But I mean, the typical thing is you get the bound state if you have a vortex for, say, a topological chiral P-wave superconductivity. And as I showed you, kind of the BDG Hamiltonian, right, separates very nicely into blocks, where some of the blocks simply describe a chiral P-wave superconductor. So I would expect the behavior to be very similar to normal chiral P-wave superconductors, and that you can get the Majorana bound state if you have a vortex. Another thing which we have kind of been thinking about is, if I told you that you require some lattice matching, right? And I also told you that the chirality depends on the magnetization of my antiferromagnet. So you can imagine that if you have some lattice mismatch, you will get some regions where, say, you have plus chirality here, minus chirality here, and then there's some kind of domain wall here, right, between the two, just because there is some small lattice mass match. And then I could imagine that you have now Majorana edge modes. And this is now the infamous green. Two of them at this interface because you jump from chirality +1 to -1. So this is a bit speculative at this point, but okay, still some interesting idea, I think. And maybe you can draw some picture like this, where one goes around here, one goes around here. So you can have some sort of network of Majorana edge modes. Okay, this is, you know, at least something which I find funny.
Right, shall we thank the speaker again and all the speakers in this morning? Is there any announcement?
No, I was just going to say next week, Evan will lead some discussion. We haven't set the day yet, but probably Tuesday or from then on.
Okay,
All
yeah.
right, great. And on magnetic interactions at interfaces or something like that.
Yes, my first slide maybe is a good starting point. Yeah.
All right, great, wonderful.